La la la. All right, it's working. I did plug it in, right? All right. I will begin with a word of prayer. So, dearly Father, we thank you for this day. We thank you for your mercy and love for us, for the forgiveness of sins. We just thank you for this class. I just pray you would guide our steps today, help us to glorify you in what we do. We also pray for this country, as there's obviously great evil in many places. People would choose what is evil over what is good, and that makes us sad. At least makes me sad. But anyway, I just pray you be with this class, help us to glorify you what we do this day, Lord. In your name I pray. Amen. I mean, we had 3 states, I think, if I remember, who my mom just told me, openly advocate for the murder of children in mass.
Mass murder?
Abortion. Yeah. Okay, so let's see here. I mean, California, Vermont, and I think New York.
Wow.
No surprises, really.
Wait, what were the 3?
I think California, Vermont, and New York.
PA is honestly one of them.
Was it PA?
Wait,
PA as well? Was it PA?
I have no. I think.
No.
I
I don't know. I grew up in upstate New York, so like New York's a weird thing.
Yeah.
A lot of upstate New York is fairly conservative.
It's just the city. It's
but-
the city with the highest population.
Yeah, New York City and the university centers are different. Okay, so let me do a problem for you guys. I want to work something like number 5 in homework 12. So this is like number 5 from, and let me just write it out here. So you're supposed to find the decibel rating of sound. Decibel rating of a sound, and here's how it's given. It's equal to D is equal to 10 log of I over I0. All right. So the decibel rating is typically made, so the way it works is it's typically a comparative system, all right? So you're comparing a given signal to another signal, and you use a log scale. Now, the reason this is done, a logarithmic scale is used for a lot of measurements. Like, did you guys have any idea how much greater the intensity of light is outside on a sunny day versus inside here? If I could close the shade. Do you know what like if there's 1 unit of luminosity outside, I mean, for every 1 unit of luminosity in here, like how many would you expect the corresponding units of luminosity outside are there? You say 15? Right, that's not how it works though. It's something like 10,000. And so something of this nature where you're comparing different signals which have vastly different values, orders of magnitude different, decibels becomes a useful scale of measurement. Hearing is also this way, like the sound of a jet engine, something like 100 decibels versus ordinary speech is what, like, I forget, but not 100, like 30 or something. Or anyway, the point is, that doesn't mean, if let's just suppose I'm speaking to you right now at 30 decibels, right? It's not that a jet engine is 4 times louder, right? It's hundreds of times louder in terms of like energy per square meter that the jet engine delivers to you as rarefractions and refractions of air, right? Pressure waves, which we call sound. So decibel rating is the way to go, because if you use a common log, then for every like order of magnitude, you increase your decibel rating by, well, let's see. Let's see here. So here's the problem. Number 5, find the decibel rating of a sound. You're given this formula, and with the intensity of the sound being 10,000 I naught. All right. Okay, so that's part A. So we'll do that to start with. How do we calculate that? So let's do it. So D equal to 10 times the log. What kind of log is this? It's a common log, right? This is a base 10 log by our convention. So see the I naughts cancel, and what are you left with? And as a power of 10, that's what? 10 to the what? 10 to the fourth, right?
Yep.
All right. It's not quite for the trash can, but it's definitely not for lecture. Let's stick this over here. Some unknowing, unprepared lecture to use in a future section. Let's see here. So what we got is what? 10 times 4, right? So we get 40, I think, dB, decibels. And sometimes the D is not I think the D is not capitalized. Well, anyway, it just says that they don't put the dB on. They're just like the decibel rating is 40, okay? So. Okay, so then here's part B. Find the decibel. Oh, wait a minute, what? Oh, sorry. I'm looking at the printout from the homework, and it's weirding me out. It's got A, B, and then it goes back to A again, and then it goes, so it's got, what's going on? Oh, I see. It states the question, then it states the question again. I'm just misreading it. I'm an idiot. So part B is if the intensity of a sound is tripled, how much does the decibel rating increase? So B, suppose, let's say I2 is equal to 3 times I. So what's the decibel rating? Is it 120? The answer is no. Let's see what it is. So we calculate D. Let's call it D2, 10 log of, let's see here, that would be 30,000, right? I naught over I naught. So we have to do what? This is going to be 10 log of 30,000. And so one way we could do that would be 10 times, I mean, yes, you could just plug it in your calculator, but I think it's instructive to do it this way. This is log of 3 plus the log of 10,000, right? Which is 10 to the fourth. So basically the answer is 40 plus 10 log 3. So whatever the increase in the decibel rating, it's coming from this 10 log 3 term, Anyway, let me get my calculator and work that out for us. Let's see here. See here, log of 3. Log of 3. Oh, come on, why is it doing that? Log of 3 is about 0.477, so I'd multiply that times 10. And so what I've got here is 40 plus 4.7712. So the answer is 44.77 decibels, basically, approximately, yeah. So it did not triple, right? It just increased by 4.77 decibels. Yeah?
Yep.
Wait a minute. Oh, so I'm looking at the answer in the book, and it says it doesn't have 4.77. Well, first of all, this is we have to read the question carefully. It said, by how much did it increase? So how much did it increase? The answer there would be 4.77, right? That's I2 minus I. But if I read the instructions more carefully still, what does it say? It says, yeah, round to the nearest integer as needed. So if I have to round to the nearest integer, this is 5. That's the nearest integer. So anyway, this is problem 5 in your homework. Yeah, problem 5 in week 12. The next one, problem 6, is about an earthquake. Earthquake is another thing that's measured on a log scale called the Richter scale, right? Mm-hmm. So like I'll work another one of these and then we'll go on here. So example 2, the Richter scale is log, log base 10. Now they put the base 10 on it, doofuses. It's log of I over I naught, where I is the amplitude registered on a seismograph 100 kilometers from the epicenter of the earthquake. Seismograph, 100 kilometers from epicenter.
Why do you call it a Richter scale if it's spelled Richter?
It's I'm assuming because Mr. Richter invented it. That's usually the generic answer I give, whether or not makes sense or not.
Okay.
You know? Like, why is a meter called a meter? Mr. Meter, of course.
Oh, that makes sense.
You know? Why are seconds?
It's the second.
Miss a second, actually.
Oh, really?
Yep. Thought I was going to zig, but I zagged. What can I tell you?
You said you got me back.
I got you.
Yeah.
No, really, I think there's a dude named Richter, but anyway.
Yeah.
Um,
Probably Steven.
Steven?
Yeah, Steven.
Someone Googling? Or is that, okay. So we went to this piano recital, a couple of my kids taking piano, and we went to the recital. Charles Francis Richter? Okay. And in the recital, the pieces weren't titled, but they were all like theme music or music from a famous movie or show or something. And so then the idea was people were going to write down the name of the song and like the movie or TV show or whatever it was from. And then there was going to be like prizes given whoever got the best. But in a room full of adults with cell phones, like, it's not interesting because everyone just opens up the Google and listens to it and reverse searches the music from the song. And so that's how my children won. They had my phone. But they tied another guy who was sitting there using, what's it called?
Shazam.
Yep, that one, Shazam. All right, let's see here. So we're supposed to find the Richter scale rating for an amplitude find Richter scale rating for amplitude reading of 100 million I naught. The magnitude R measured on the Richter scale is what? So basically take this number. This is 10 to the what times I naught? How many zeros you got? 1, 2, 3, 4, 5, 6, 7, 8. 10 to the 8th. Right? 10 to the 8th. So the Richter scale measurement log of I over I naught is log of 10 to the 8th I naught over I naught. So of course those cancel and we get log of 10 to the 8th, which is equal to 8. So this would be not an earthquake you want to be near to, right? These are bad. We had, you know, any of them? You know, we had an earthquake here, I don't know, like 10 years ago, something like that. I was just sitting in my office and I felt like, you could actually feel it here. It was like, what? It's so weird because we don't really have earthquakes on the East Coast much, right? So, but it did some minor damage to some houses, like out in the country here, but for the most part, it was kind of inconsequential. All right, so those are the problems I wanted to work for you guys because we haven't done anything like this, right? But this is one of the reasons logarithms are interesting, is anytime you're dealing with data which has like a very vast, if your data spans over like orders of magnitude, using a log scale allows you to like compare such values in a meaningful sense. And that's why in like your science classes you might use like a semi-log plot or something. That's a plot which uses a logarithm for this is you, right? Uses a logarithm for one of the axes, but not the other, something like that. Okay, oh, sorry about that. Anyway, any questions about other homeworks? Otherwise, I will go on, do more homework problems, all right? So let's see here. Let's do number 7 in the homework, yeah? Example 3. It's kind of a warm-up problem. It's not that interesting. Log base pi of 42. That's weird. So how do you calculate this? It says to use the change of base theorem. I always call it the change of base formula. All right. And so here, what we do, the change of base formula, we can use natural log for it. Natural log of 42 over the natural log of pi. Now pi is a number, right? 3.141596622. Oh, what? You know it? Oh, rats. You know more than I do, so I can't make, I usually make it up after the 5th digit. Dang it. Yeah, somebody in my other section had a middle school teacher who taught her to like, you did 100. Yeah, she was also, she memorized 200, she said. But she'd forgotten all of them, but like the first 10.
I got up to like 40. And then I gave up like.
Hmm.
You can just make it up.
Interesting. All right, so plugging it into my calculator, what do I got? Yeah, I get approximately 3.265. Now, I should probably look at the instructions. What does it say? It says simplify your answer. Do not round until the final answer. 4 decimal places. Okay, so 2651 would be the answer here. Yeah, just that's my calculator. This was number 7 from week 12. Number 8, I'll work next. Suppose you got natural log of like the square root of a squared over b cubed. How would you, what are we supposed to do here? We're supposed to simplify this, and you're given, ooh, I like this. I like this problem a lot. You're given u equals natural log of a, and v equals natural log of b, all right? And you're supposed to write the expression that's given in terms of u and v, all right? So how do we do that? So let me break it down into a couple steps, okay? So we're dealing with the natural log of the square root. Square root is the what power? 1/2 power. Very good. So that's natural log of a squared over b cubed to the 1/2. Right?
Mm-hmm.
So yeah. Sure.
How do you get the ln on your calculator?
Natural log.
Yeah. Like, how would I get, like, does my calculator work for it? Because I was trying to do the problems.
Can I just hold it for a second?
Yeah.
It's here. It's this one.
This one?
There you go.
Oh, okay.
Uh-huh.
Thank you.
It's weird. Looking down on your calculator, there's like a glare from the light up there. I couldn't see the shine of the buttons, but also I need glasses. Anyway, so we pull the half out, right? So by properties of logs, this is 1/2 natural log of a squared over b cubed. And then we can use law 3 of logarithms we proved Monday, right? Which is that when we have a fraction, we subtract the log of the numerator, which here is a squared, and then we subtract from it the log of the denominator, which here is b cubed. But then, by property 2 of logs that we proved Monday, we can pull the powers out, right? So I can pull a 2 down, and I can pull a 3 down, right? So this comes out here, and that comes out there like that. In particular, I have 1/2 times 2 log A minus 3 log B. Then multiply the half through. What do we got? We've got natural log of A minus 3/2 natural log of B. Everybody with me? So then what? What's the answer here? How can you write the given expression in terms of u and v? What do you guys think? Yeah, natural log of A was given to be u, right? So this is u minus 3/2 v, and that is the answer that the book or your homework system is looking for. That's it. U minus 3/2 v is the answer.
And
That's number 8. Your number 8 might have different powers, and it might have a cube root, I don't know, but your number 8 should be something like that. Okay, let's move on here. I'm going to skip ahead. We worked some harder equations last time, right? Here's one I don't think I did yet. I don't think I did this one yet. Let's try this one out. Number 15. It's a little bit ugly. It's 3 times 1.21 to the x power plus 1 equals to 15. How are we going to solve this thing? What do you guys think I should do to start with? What should my opening move be on that problem? I mean, certainly we can subtract 1 from both sides, right? Definitely you don't want to take a natural log at the start of it. See, if I just took a natural log of the equation as it's given to me, what would that get me? Let's talk about that. Sometimes it's important to talk about why you don't do something. Why don't I just take natural log of both sides? I mean, that's true. You could do that. But does it help? It doesn't help. The reason it doesn't help is there is no nice formula for log of a sum. Log of a sum is a dead end. There is like nothing to do here. All right, nothing to see here. This is not a wise move algebraically. It's just a dead end, right? On the other hand, if I subtract 1 to the other side first, right? Now this equation, if I take the natural log of that equation, something pretty nice happens. So how does that go? Natural log of 3 times 1.21 to the x equals to the natural log of 14, right? Natural log of 14, it is whatever it is, right? But how does the natural log of 3 times 1.21 to the x power simplify on the left-hand side? What are the properties of logs we can use? This is what? This is log of 3 plus the log of 1.21 to the x power, right? Using property 1 of logs that we proved last class, right? Log of a product is the sum of the logs. And then I can pull the x out, right? Because x is a power. But it's important. I cannot, something I should have mentioned here, and this is something students often get wrong. Up here, no. You cannot just pull the x out here. Why? Because this is not multiply. It's not all of the input to the log raised to the power x, right? The 3 is sitting here. It's not raised to the x power. It's not the right pattern. Like the log law that I'm referencing is this one. Log of something like a to the power p, right, is p log of a. It's important that the whole whatever you're looking at is raised to the power p. You can't just have it on part of it and not all of it. It has to be the whole deal. So like I can't pull the x out here. It is not allowed. It would get you the wrong answer. But I can pull x out down here because now it's the whole thing raised to the x power going into the natural log, right? So that is an appropriate use of that property. So I got log of 3 plus x times the log of 1.21 equals to the log of 14. And now at this point, I have an equation which involves x and logarithms. But the thing is, these are just numbers. You can find them on your calculator. So solve for x. Can you guys solve for x at this point? Isolate it, right? So we've got x natural log of 1.21 equals log 14 minus log 3. And then divide by log 1.21. Here it is. X equals 2 log 14 minus log 3 divided by the log of 1.21. And that is the answer. Did any of you guys do this problem a different way? Yeah.
Someone got the ln 3 plus the ln 14?
That's possible. But did you get a minus on it?
I think I just put like -3 plus.
Oh yeah, -3 plus is fine. There's another thing you could have done.
Did you technically have divided by 3?
Ah, yes, this is what I was hoping for. So you're like, I could have 1.21, but you didn't do it. You're thinking about it though, right?
No, I probably just divided it first and got it x.
Yeah. So this is exactly. This is what I would have done as a student. Probably when I was in your place, I would have just divided by 3 and then taken the natural log. You know, and that's also fine if you do that. Well, yeah. So when we take the natural log of this, we get x times the log of 1.21 equals to the log of 14 over 3. Right? But what is the log of 14 over 3? It's the log of 14 minus the log of 3. So it's really the same answer. Like this, you could simplify to the natural log of 14 over 3 divided by the log of 1.21 if you wanted to. And if you want something unambiguous there, calculate the decimal. Right? So sometimes on these, I will ask you for 2 answers. I will say, please give me an answer both as an exact expression using logs, all right, and as a decimal. So here's, the thing is, the answer as an exact expression involving logs, that's not a unique thing. There are many different ways to simplify the log and collapse things down. And sometimes, on first glance, it's like, wait a minute, is this equal to that? Like, unless you have, like, ingrained in your mind the identity that the log of a difference, the difference of logs is a log of the quotient, then you wouldn't see that those are equal, right? Anyway, so what is this? It's log of 14 divided by 3 divided by log of 1.21. And I get 8.0812. So there you go. There's that problem. It is important that you have a calculator for the next test, right? Like, you need to have a calculator, you need to know how to use it. And it cannot be a graphing calculator, so let us make sure we have addressed those issues before it's test day, yeah? Let's look at another one. Example 6. So this one is like number 17 in week 12. This one's a pretty easy one, but it's a good starting point. So here we go. 2 natural log. I may have already done this one last time. If I did, my apologies. We'll do it again. All right. We might have done this last time. I can't quite remember. If we did, I'm sorry. So, hey, tell you what, to be safe, I'm going to change that 10 to a 40 there. I'll make it different. Okay. Now it's different for sure. How do you solve that? This is like number 17, yeah. How would you solve this? Divide by 2 first. I like it. 40 over 2 is 20, right? What's the, yeah?
Are you trying to get the x by itself?
I am. I'm trying to solve for x, yep.
Should you divide that ln?
Ooh, we cannot divide the ln. Dividing the ln is no allowed. Ln, remember what ln of x means. I mean, I know this notation, right? What does that mean? This means we're feeding x into the natural log function. So it's not a multiplication by letters ln n. It's actually, that's a notation for saying we're putting x into the log function, right? Mm-hmm.
Exponential form where it's e to the 20
Right. You could put it in exponential form. Another way of saying that, I wanted to,
Or invert.
because I'm trying to talk about doing something to the equation. So I totally agree with you. It's just the way I'm going to put it into exponential form is I'm going to exponentiate both sides of the equation, which is to say, raise this to the e to this equals e to that.
Okay.
And see, the exponential and the log are inverse functions, right? So just this simplifies to x, and the other side is e to the 20, right? So actually, if we did what you said and just put it in exponential form, as soon as you put it in exponential form, you solved it, right? That is the solution. And
Put it in exponential form.
mm-hmm.
Then you get the answer.
Well, yeah, I mean, the exponential form of natural log of x equals to 20 is, so like, this is exponential form. And then if you change this to, well, this means that log base e of, how does it say this? Log base e of x equals to 20. This is the logarithmic form of the same equation. Listen, guys, there's always this interplay we have between like logarithmic and exponential form. So if we have something like a to the power, I don't know, y equals to x, that's the exponential form. Let me not use x and y. Let me use Pac-Man and Ghost. This is true only if log base a of Ghost equals to Pac-Man. So this is the exponential form, and this is the corresponding log form. And you can always trade one for the other, and sometimes it's helpful. But also, to get from one equation to the other, you could either exponentiate both sides, or you can take the log of both sides. Like, to get from here, right, over to here, you just take log base a. Okay? And to get from here over to here, we raise both sides with a. A to the both sides gets you from one to the other. Okay, anyway, enough about that. The answer we found like 3 minutes ago before I jibber jabbered on. Here's example 7.
Does C have to be positive in the logarithm?
Does C have,
Like, can x be negative in example 17?
well, x is equal to e to the 20th, so it's positive.
Well, no, like theoretically.
Theoretically, no.
Okay, so x cannot be negative.
It cannot.
Like, in a logarithm, can a c value ever be negative?
C value, what's a C value?
If it wasn't x, like,
Well, here, let's look at one where that's an issue. How about that?
did you have a question where it's like 2 to the common log?
Well, here, yeah, I mean, here, the question you're asking about is relevant. Let me show you one where it comes up, okay? But no, we have to have log of a positive number.
Okay.
That's the terms and conditions, because the log is the inverse function to the exponential. The range of the exponential is positive numbers. That has to be the domain of the log, no matter what the base is. But this is like number 21. So we've got log base 6 of x plus 3 times x minus 2 is equal to 2. It's like number 21. So what do you do here? So what I would do is I would raise both sides to the 6. I mean, not raise it to the 6, but 6 to both sides, yeah? Exponentiate both sides base 6, let's say. So I do 6 to the this equals 6 to the that. So the 6 and the log base 6 cancel, and that gives me x plus 3 times x minus 2 equals to 6 squared, which is 36, right? And at this point, you're like, oh, I feel much better now. Back to quadratic equations. This is what I like. Yes?
I have a question. So, how does raising it, this is gonna seem stupid, right? But when you raise it to the 6, I mean, when you raise it to 6, how does that cancel out the logs, I guess?
I mean, this is the definition of the log. So 6 to the log base 6 of, y is equal to y for any positive y. And also, not that we use this yet, but log base 6 of 6 to the whatever is equal to x. That's just for any x, yeah? So these are the two defining conditions for log base 6 and the exponential base 6 as they relate to one another. So, I mean, it's by design. By design, log base 6 is the inverse function to the exponential base 6. Yep.
So did you raise it to the 6 because it was log to the 6?
Yep. If I hadn't had log 6, like, for example, if we were up against number 19, let me put down number 19 here for a second, just so we can contrast, yeah? So number 19, come on. Number 19 in contrast is we're up against log base 2 of x cubed plus 15 equal to 4. So that one, and so yeah, we could just use we could just jump straight to the exponential form if you want, right? That's fine. I like to think about it operationally, personally. I like to think about doing things to an equation to get another equation. That's just how I'm wired. So if I raise both sides, with the exponential base 2, take 2 to both sides, then these cancel out because they're inverse functions, and I get x cubed plus 15 equal to 16. 2 to the 4th is 16, which gives me x cubed equals to 1, which gives me the solution x equals to 1. So I take the cube root of both sides. Cube root of x cubed is x, cube root of 1 is 1. So the answer is just 1 for problem 19 for me. How about going back to example 7, though? We should finish this, yeah?
Oh, I'm sorry.
Mhm.
In the video I saw, was
Oh.
the reason why that wasn't the cube root was not an absolute value is because it was odd?
Yeah, because it's odd. The odd, exactly. So the nth root of x is equal to x again, n odd, and its absolute value of x if n is even. Although I will say, in the context that we're working, a lot of times it's assumed that we're working in a positive context. So like absolute value of x might just be equal to x, depending on like the backstory to the problem in here. Yep.
So what you're saying with that formula is that like because the 1 is odd, so it was a 2. It's not.
It's not the 1, it's the 3 that's odd.
So it's whatever exponential.
It's the power. To undo the cube, I take the cube root.
Oh, okay. So it's.
Yeah, that's another inverse function. So the cube and the cube root are inverse functions. So we take the cube root to undo the cube. Just like we take the log to undo the exponential. Or the exponential to undo the log. So how do I solve this? Yeah, probably FOIL it. That's a good idea. X squared plus x minus 6 minus 36 equals to 0. And so what we got is we've got x squared plus x minus 42 equal to 0. We can factor that, right? 42 is what, 6 times 7, right? We want a plus, so we do plus 7 minus 6. Yeah. And so what are my solutions? I get x equals to minus 7, or x equals to 6. Now, any of these problems, all right? This one's probably okay, but we should really take a second to double check and make sure that when we plug it back in, it works. Does it work? If I plug back, see, because you were just talking to me about, don't you have to put a positive number into a log, right? This is a negative number. What's going on? How's it work? Well, careful. We're not putting it directly into the log, right? We're first putting it into this x plus 3 times x minus 2 expression, right? What happens when you put minus 7 into this? What do you get? I'll write it up here. You get like minus 7 plus 3 times minus 7 minus 2, right? Or you get 6 plus 3 times 6 minus 2, right? So when we plug in minus 7, we get a minus times a minus, which is a plus, right? That's okay. We can put a plus into a log. And on the bottom, we get plus times plus, which is plus. We can put a plus into a log. So
Can you put 0 into the log?
no, log of 0 is not defined. Yeah. For log of 0 to be defined, that would mean that 0 is in the range of the exponential, but that is not the case. 0 is not in the range of the exponential. Therefore, it's not in the domain of the log. So this problem wasn't too bad. Both of the answers work. A lot of the ones in the homework, we have to be careful. They don't work out like that. Yep.
I don't know if this has been asked, but is there a way for you to like open up the previous homework so we can like time these problems?
I don't know. I mean, I'll open up all the homeworks eventually, but I'm not there yet. So we should focus on week 12 at the moment. But I think you should be able to look at the previous homework assignments. If you go into My Labs and go to like previous assignments, you should be able to get into it there, right? Anybody done it? I see some nodding. How do you get to that? It's not under, what are they called? Like past assignments or something, or
Just go to assignments and then
click on past assignments.
you just click on the number. Like
Click
it says like week 4.
week 4.
5, you can open it.
Okay.
Yeah. And then whatever you do can give you like 0.5 value if you haven't finished it.
Aha. All right, so another example here. Number 22, this is example 9. Here we've got log base 4 of x plus log base 4 of x minus 6 equals to 2. How are we going to solve this one? So here's what we do. We use properties of logs to, so we do log base 4 of x times x minus 6 equals to 2 by properties of logs. And then we raise, exponentiate both sides base 4. So 4 to the this equals 4 to the that, which gives me x times x minus 6 equals to 16. Whoa. I didn't notice that before. You ever notice that? 2 to the 4th equals 4 to the 2? That's weird. That doesn't usually happen, right? Like 3 to the 4th is not equal to 4 to the 3, I don't think. I'm pretty sure not. Okay. So therefore, no, don't do this. Okay. So getting back to here, we've got x squared minus 6x minus 16 equal to 0. Can you factor that? I think we want a 2 and an 8, right? Do we want plus 2, minus 8, minus 2, plus 8? What do you think? I think, yeah, plus 2, minus 8, I think. That way we get a minus 6. So what are my solutions? X equals minus 2 or x equals to 8. Right? Now here something interesting happens, right? Are those both actually solutions? But are they solutions? Look back at our equation. For them to be a solution, they must solve the original problem, right? Yeah. And the original problem, log of x plus log of x minus 6. But what happen? We can't put negative 2 into this right here, right? So this right here is what's called extraneous. So this is not actually a solution, extraneous. Cannot put into log base 4 of x. And I mean also, of course, the other one also gives you negative, right?
Yeah.
You log a minus 8 for the other term, yeah? So this is kind of, remember before when we square equations, sometimes we bring new solutions in? Something similar happens here when we use the log property. Technically, the log property only holds true when what? When both inputs of this log and that log are both positive, right?
Okay.
But when you just combine them like this, right? And then you look at what are possible ways to solve the next equation, well, you're automatically going to get when they're both negative, because both negative gives you a positive, and that's okay. That was okay over here, right? Because over here, we never had the first thing, right? We never had separated log base 6 of x plus 3 plus log base 6 of x minus 2, right? That would have been a different problem. So, but anyway, so Friday we will continue doing these problems. I pretty much showed you all of the techniques. We'll just work more problems. So, thanks, guys. You should be able to get to those problems from like the past problems.